Okay, this is Coach Williams, and we are in calculus working with linear approximations. We started this and we had an announcement interruption, so we had to restart the video, but we're talking about linear approximations. And it wants us to describe the lines of each function as above or below, and that's going to be key for us as we move along through linear approximations. If we draw a tangent to this curve here, this is some function f of x, and we say we're going to draw at this point. This is our line coming across there. All of the values on this line are going to be, with the exception of one point, are going to be below the value of the curve or the function. So this one obviously is going to be below. Again, if I have a tangent line on this other one, let's say we draw a line coming across there somewhere, and we've got a point. Again, this is going to be below. And so we're going to find out something here in a minute about characteristics of the parent function and when we draw tangent lines and what our approximations will be. But the tangent lines here, tangent lines below the curve. And that's pretty easy to see, pretty straightforward. On the next one, this is going to be where the function's concave down. This would be concave up, but in concave down situation, if I drew a tangent line going across there, or let's say I had a tangent line I'm drawing going across there, either way, again, the tangent line or lines are above the curve. And thus, if I didn't have the exact value that I'm looking for, but I'm trying to get close to it on the curve here, my approximations is what this is getting at. My approximations would be a little bit high, being that the tangent line is above the curve. All right, so, and this goes on to kind of explain that here. Linear approximations. The use of the tangent line at a f of a as an approximation to the curve y equals f of x when x is near a can be explained in this right here. You've got the equation of the tangent line is going to be this. Y minus, and if you look at this, this looks very much like our formula or form of the point slope form. Y minus y1 equals m times x minus x1. Does that look familiar to you? This is our point slope form. And if you think about it, here's our point, isn't it? I mean, a is the value. When we plug a into the function, that's the y value. That's the output value, so our input and output values. And so now we're just taking y minus the output value. And the derivative of f of a, that is our slope. That is, the derivative at the point a, that is the slope of the tangent line. And then times x minus the input value a. So that is the exact form that we're talking about. The linear approximation says that, well, f of x is approximately f of a plus f of the prime of a times x minus a. So this process is called linear approximation of f at a. Let's do an example here and see if this begins to make a little more sense to us. Okay, it says use linear approximation to find the value of f at 2.97. And this is our function that we're dealing with. Now, when we're looking at this function, we're probably going to have to use some of our rules that we had in the past, but let's just look here for a second. The first thing it says use linear approximation to find the value of f at 2.97. 2.97 would be a hard number to throw in if we're going to be squaring and cubing and doing all these things. But what we could do is say, well, what about 3? 3 is really close to 2.97, so let's look at 3, and then let's see if our approximation, once we do get it, is it going to be high or low? And that's what we're going to, that's the concept that we're trying to establish here. So looking at this, the first step that we need to do is we need to find the derivative of f of x. And at this point, I'm just going to distribute this in. Instead of doing product rule, I'm going to distribute this in. This is the same thing as 4x cubed plus x squared, is it not? If I distribute the x squared into the parentheses. So now, using the power rule, the derivative of f of x is going to be what? 12x squared plus what? Plus 2x, exactly. Plus 2x. All right, so now we're going to choose a whole integer, right? Whole number to work with is a little easier to work with. We're going to choose x equals 3, and then we're going to plug that in. So if I plugged in f prime of 3, right? This is our tangent line, the slope that we're looking for, derivative here. So if I plug a 3 into that equation, not the original, but into this equation here, which is the derivative, then I should get 114. So now, let's do this. This is pretty cool. I know that f prime of 3 is 114. What would f of 3 be? F of 3 was, if I plug that in, 3 into this right here, you can do it in your calculator, it should be 117 actually. So I have a value that is, let's say, f of a, right? We talked about f of a up here. F of a, so we plug it into the original, and then we also plugged it into the derivative. This derivative gives us what? What is this giving us? Slope. Good answer, good answer. This value is giving us what? We've got an x value, and this is our y value. This gives us our point 3 and 117. Correct? So this gives us our slope when we plug it into the derivative. When we plug it into the original function, it gives us a point, y value basically. We know the 3. It gives us the y value for our point. So now we have 3 and 17. Can I write that equation out now? Can I say, okay, y minus the y value, 117, equals 114, which is the slope that we found, times x minus 3. Isn't that correct? So then, let's simplify this or solve for y. And can't we say y and f of x are the same thing, right? So let's say y equals, we're going to move the 117 across, which just means we're going to add it, right? So it's going to go away there. So y equals 114 x minus 3 plus 117. And really, we could just say that's the same thing as f of x. Okay, now that we have this equation, this is the beautiful part of it. We have this equation for the values when x is 3. We can use this equation, and at this point, we could plug in 2.97, and we plug in 2.97, it's going to give us an approximation of what it should be. Now remember, we did the whole equation with a 3. So it's not exact, but it's really close, is it not? I mean, 2.97 is really close to 3. And so we look at this and we say, okay, well, what is f of 2.97? And we just simply plug that in where we see the x. Right? We're going to plug in 2.97 where we see the x. Then we're going to add 117. And what we find out is that it is approximately 580, right? 113.580 if we plugged in the calculator is what we should get. And so look here, when we plugged in a 3, we got 114, but 2.97, obviously a little less than 3, right? Gave us 113.580. Now, when we look at this and we try to graph it, we put this in the calculator would be the easiest thing to do. We put this in the calculator and we graph this. We're going to see that the graph looks something like this. It's going to come up here, come down, and go up like this. Okay, so at 3, when we put a tangent line on the curve here at 3, what is this going to be? Is it below the curve or above the curve? It's below the curve, right? Since it's below the curve, the B part of this example, our approximation is going to be low. Is it going to be high or low? It'll be low because the tangent line is below the curve at x equals 2.97. So at that value, x equals 2.97, we know the tangent line's below the curve. Okay, so this is, let's say this is 3, right? So before that, right before that, we know that this line's below this curve, so our approximation is going to be a little bit low. Okay, so hopefully this kind of gives you a better understanding of what we're doing. We pick a number that's close to the number they're asking us to use, right? Pick a whole number that's close. We go ahead and find the slope. We find the equation of that tangent line. And once we get that slope and tangent line found, then we plug the real number back in, and it should give us a pretty close estimate of what the value would be at that point, even though it may be a long decimal of some kind, some number. Okay, all right. Let's look at the back. We have example 2 here. Suppose the only information you have about a function is that f of 4 is a -2, and the graph of its derivative is as shown. We want to use linear approximation to estimate f of 3.9. And is your estimate too high or is it low? And explain it. Okay, so obviously we have that we only know that f of 4 is equal to 2. Well, 3.9 is pretty close to 4, so why don't we just choose 4 since we already have a value for that. Let's spell choose correctly. Choose x equals 4. All right. Now, f prime, let's find some things out that we do know. F prime at 4. Let's see. 1, 2, 3, 4. F prime at 4 is what? 1, 2, 3, 4, 5, 6. Okay. This is 4. So f prime at 4 is a 6. Okay? And if I plug in, if I have 4 in the original function, I get a -2. Is that correct? So in the original function, I know I've got a point at 4 and -2. Correct? And this is just taking information that I know. Once I kind of build this information up, then I can assess, okay, well, what can I do with it, right? So I've got a point at 4, -2. F prime at 4 is giving me what value? It's giving me 6, but what is that? That's the slope, right? So if we plug in a number in the derivative, that f prime is called the derivative. So if we plug a value into that derivative function, that's giving us the slope. So do we not have a point and a slope? Right? So now can I write this equation out? Can I say, okay, well, y minus a -2 or plus 2 equals 6 times x minus 4. That's absolutely doable and understandable. So we can now simplify this one down to where we'll take that and be making an f of x. We'll move the 2 across, so it means we'll minus 2 from both sides. So 6 times x minus 4 minus 2. And then at this point, I have a function, right, or an equation of this tangent line that I could plug in 3.9, and I know I'm going to be pretty close. I know it's not going to be exact, but I'll be pretty close to that curve. The line's going to be off just a little bit, but I'll be pretty close to the curve. So if I plug in f of 3.9, then I'm going to get approximately, right, 6 times 3.9 minus 4 minus 2, which ends up being approximately negative 2.6. Now again, I don't have the original function or anything, but I've used some information that they gave us and that we know about. This is the derivative, the graph of the derivative, so I can go to 4, find the slope, right? Find the slope, it's a positive 6. And so let's look now at what we have. Let's think about this for a second. If this is the derivative function, right? This is the derivative function. What do we know about, let's just say, what do we know about the derivative first? Let's do a sign analysis here. So we can kind of find out if we got a curve going concave down or concave up. We know that at whatever point this is, we'll say it's at, what is it, 1, negative 1? So at negative 1, and then at 5, 6, and we'll just say 6.5, right? So at negative 1 and 6.5, we have two zeros, or two, like a min and a max, correct? We got a min and a max probably. And we know that it's positive on the derivative function. We know it's positive here. We know it's negative and negative, right? So we know that, okay, if the slope is negative, 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 and at negative 1 it becomes positive, then on the original function at these same locations, we know that it's decreasing, it's increasing, and it's decreasing again, right, at those values. So we know that, that being the case, here's negative 1, here's 6.5, right? We could even throw in 4 over here in a minute, but that's 6.5, that's negative 1, that's 4. We know that there's a, yeah, what did we say here at negative 1? Yeah, negative 1's a sign change. So we know it's curving at negative 1, it's got to be a min, right? Because when you're decreasing, you start to increase, you have to have a min. We know it's increasing, increasing, increasing until it gets to a 6.5, and then it's going to have a max. So now we have a graph that we can see of the function, the f of x, right? So at 4, is my tangent line above the curve or is it below the curve? Yeah, my tangent line's above. So my approximation, right, is going to be too high, or just, it's going to be high, because the tangent line is above the curve at x equals 4. Okay, let's move that up where you can see that. It's going to be too high because the tangent line is above the curve at x equals 4. And doing your sign analysis is going to help you determine your concave ups and downs, and that way you can find out if your tangent line's above or below. Okay, so hopefully this gives you another video to watch or re-watch as you go and do some of your practices. And I hope this helps you guys out. We'll see you next time.